Swayam Prabha. Digital India. Educated India.
Hello everybody. We have now looked at all the fundamentals that are required for performing material balances. So now in today's class we will talk about performing these material balance calculations for single unit systems which do not have reactions. These are the simplest possible systems. There are many types of processes which are actually just single units and non-reactive. We will go through some examples of these processes and try and solve problems related to these processes. The first and the simplest of system is a divider or a splitter. The flow chart shows what a divider or a splitter would be. You have one splitter feed which is then divided into multiple splits. You can write a total mass balance which is A, which is the splitter feed, equals B plus C, which are the splitter exits. You need to understand that the composition of stream A, B and C are the same. So a simple example would be, consider a 10 grams per liter solution of NaCl flowing through a pipe. If you were to divide this one stream into two or more streams, the concentration of sodium chloride is not going to change. It is only going to be the flow rates that are going to be divided. So the concentration of all these three streams will remain the same. Because of this, only one independent balance equation can be written, which is the total balance equation. If you were to write the component balance equations, they would be dependent on the total balance, as all the concentrations will be the same and get cancelled off. Now let us try and solve a simple example problem which illustrates this. Here is an example problem which illustrates what we just learnt about the splitter. A stream of growth medium containing 60% glucose and 40% growth factor A is flowing at 500 kilograms per hour and is being divided into two feed streams for different cell cultures. 1/4 of the growth medium was sent to fermenter 1 and the rest was sent to fermenter 2. You have been asked to calculate the flow rates of glucose and growth factor A in the feed streams for the two fermenters. As I had mentioned earlier, the first step for solving any material balance problem is to identify a convenient basis. When we read the problem statement, we find that 500 kilograms per hour of feed is entering into the system. This information has been provided to you. So you would use this as your basis. So we start off with basis is 500 kilograms per hour of feed. Now the next step is to draw a flow chart which would clearly represent the process. So you have one feed stream which is flowing at a rate of 500 kilograms per hour and contains 60% glucose and 40% growth factor A. So this is divided into two streams which we call as the splitter exits. So the first exit we will say that has a flow rate of F1 kilograms per hour and the second one can have a flow rate of F2 kilograms per hour. The problem statement says that the feed entering into the splitter has been divided into two streams and 1/4 of the growth medium goes to the first stream and the rest goes to the second stream, which means 3/4 of the feed entering would go into the second stream, indicating that the value for F2 would be equal to 3F1. So instead of writing F2, we would be better off writing 3F1, which incorporates the correlation between F1 and F2. As we already know, the splitter makes sure that the flow is split into multiple streams, but it does not affect the concentration of the substances present in the stream. This means these two exit streams would also contain 60% glucose and 40% growth factor A. So the concentrations or the compositions of these two streams are 60% glucose and 40% growth factor A. The same goes for the second stream also. Now, to solve for F1 and F2, or we would have to write the total mass balance equation. So, the total balance equation would be, you go back to the fundamental equation, which is accumulation equals input minus output plus generation minus consumption. In this equation, the system is at steady state, which means accumulation term goes to 0, and you have an input term, you have an output term. There are no reactions happening, which means the generation and consumption terms also go to 0. So, the equation can be simplified as input equals output. When we write this equation using the flow rates given, we would simplify it as feed, which is 500 kilograms per hour, is equal to F1 plus 3F1. So, this gives you the flow rates as F1 equals 125 kilograms per hour and F2, which is equal to 3F1, is equal to 375 kilograms per hour. Now that you have calculated the total flow rates of the two exit streams, you have to go about and look whether that is all that was asked in the question. When you check the question, you find that the question asks for the flow rates of glucose and growth factor A in the feed streams to the fermenters, which means our calculations have not been complete. So, we need to now calculate the amount of glucose and growth factor A present in the two streams. So, we already know that 60% of the streams would contain glucose. So, this implies for stream 1 and stream 2, the amount of glucose would be 0.6 times F1 and 0.6 times F2 respectively. So, in stream 1, the mass of glucose leaving would be 75 kilograms per hour, and in stream 2 it would be 225 kilograms per hour. So, 40% of these streams contains growth factor A, which implies stream 1 would contain 0.4 times F1, which is 50 kilograms per hour, and stream 2 would contain 0.4 times F2, which is 150 kilograms per hour. With this, our calculations are completed. We know that the mass flow rate for stream 1 is equal to 125 kilograms per hour, out of which 75 kilograms per hour is glucose and 50 kilograms per hour is growth factor A. For stream 2, the total mass flow rate is 375 kilograms per hour and the glucose flow rate is 225 kilograms per hour and growth factor A flows at 150 kilograms per hour. With this, we can try to move on to the next system. Mixer is another common system which is used for any process. Here what happens is you have more than one input and there is one final output. So, multiple streams containing different components are mixed together to form one final output, which is the mixer product. So, here you have multiple balance equations you can write. Can you identify how many independent material balances you would be able to write for such a system? Obviously, you can write the total balance equation and you would also be able to write component balance equations. So, would all of these be independent or would one of them be dependent on each other? What you would find is the summation of all the component balances will be equal to the total balance. So, the number of equations which are independent that can be written for a mixing point would be equal to the number of components that are present in the system. Here is an example problem which we will try and solve to understand the principles behind material balance in a mixer. Primary antibody deficiencies are treated with subcutaneous immunoglobulin replacement therapy. This SCIG product contains 10% IgG, which is a type of immunoglobulin, and 5% sorbitol, and the rest is water. This mixture can be prepared by mixing a concentrated IgG solution which contains 50% IgG and the rest water, a concentrated sorbitol solution containing 40% sorbitol and the rest water, and pure water in the correct ratio. How much A, B and C, which are the 3 different solutions that need to be mixed to produce 10 liters of SCIG product? You can assume that the density for all the solutions is equal to 1 grams per centimeter cube. Now let us try and solve this problem. Where do we start? The first step for any material balance problem, as I said, is identifying the basis. Here the basis would be 10 liters of SCIG product which is formed. I had also informed you earlier in the previous lecture that we should avoid volumetric flows and volumes as for balances. So we should convert this volume into mass before we proceed and perform balance equations. So the basis which we use for this system would be 10 liters, which can then be converted to mass using the density. So this 10 liters using the density of 1 gram per centimeter cube can be converted to mass. That would be by 10 liters times 1 gram per centimeter cube times 1 kilogram per 1000 grams times 1000 centimeter cube per liter. So now your liters get cancelled off, your grams get cancelled off, your centimeter cube gets cancelled off, and you are left with mass in terms of kilograms, which is 10 kilograms. Although this conversion is simple, I have still followed a meticulous pattern of writing down all the units so that I ensure that there is minimal chance of error. So this kind of a systematic problem solving will ensure you do not make mistakes like dividing the conversion factor instead of multiplying or vice versa. So now that we have the mass, we can write total balance equations. So we know that there are 3 streams which are coming in. So the flow chart would look something like this. We have 3 streams which are entering into the mixer to finally form one product. So if this is the mixer, we have 1, 2 and 3 input streams and one final output stream. Let us call these as A, B and C. We can label these with the information on the concentrations which have been given. So A has been told to be 50% IgG and the other 50% is water. B is 40% sorbitol and the other 60% is water. C is 100% water. Your final product which you have formed, which we will call as P, is 10% IgG, 5% sorbitol and the rest, which is 85%, is water. Now that we have all this information in the flow chart, let us try and calculate the actual flow rates for each of these streams. The total balance equation can be written as input minus output plus generation minus consumption equals accumulation. Again, being in steady state, accumulation will go to 0, no reactions, so generation and consumption go to 0 and you end up with input equals output. So the input here are A, B and C and your output is your product, which is 10 kilograms per hour. Now after writing the total balance, we can now write the component balances. So let us start with, let us first start with IgG. When we write the IgG balance, we would have 0.5 times A is equal to 0.1 times the product, which is 10. So again I have used the same equation, which is input minus output plus generation minus consumption equals accumulation, and considering steady state and no reactions, we have gotten input equals output, and from this we can calculate the value of A as 1 divided by 0.5, which equals 2 kilograms. And writing a balance equation for sorbitol, we would be able to get 0.4 times B is equal to 0.05 times 10. So, based on this you can calculate B as 1.25 kilograms. So, substituting these two values in your total mass balance, you would be able to calculate C as 6.75 kilograms. So, these are the masses which have to be mixed to get your final product, which is 10 kilograms of SCIG product. So, you can also convert them back into volume, so that you can give the values as liters instead of kilograms. So, the values would be 2 liters, 1.25 liters and 6.75 liters of A, B and C, finally giving you a total volume of 10 liters of SCIG product. So, you can actually verify whether the answers you got are correct. So, the last slide which we looked at when we saw performing the fundamentals for engineering calculations was validating the answers we arrived at. One possible way to do it would be to use different equations and perform the calculations using a different approach. So, here what we can do is we can write a component balance for water and try to solve and see whether we get the same values. So, we can plug in these values to the water balance equation to confirm whether our answers are correct. So, if we were to write a water balance equation, it would look like this. You again have input equals output. So, input is 0.5 times A plus 0.6 times B plus C, which will be equal to 0.85 times 10. Now, these values of A, B and C can be plugged in to see whether this equation is valid. So, your left hand side would now become 0.5 times 2 plus 0.6 times 1.25 plus 6.75. This adds up to 8.5 kilograms. Your right hand side is 0.85 times 10, giving you a value of 8.5 kilograms. So, your left hand side is equal to your right hand side, thereby showing that the calculations you had performed and the values for A, B and C that you obtained are actually correct. Now, let us consider a different process, drying. Drying is a process where you have one feed which enters into a dryer, and this system gets heat supplied to it, thereby some of the solvent gets evaporated and you end up with a dried product. The wet feed which enters into the system can be a solid, a solution or a slurry. The solvent stream is a vapor which is solid free. Only the solvent gets evaporated and leaves the system as a vapor. The solids do not accompany this solvent stream which leaves the dryer. The product stream is a solid, however, it does not have to be only the solid. Some of the solvent may still be present in the final stream, because not always are the feed fully dried and you end up with a bone dry material. You might want to just reduce the concentrations. Another process is an evaporator, which is very similar to drying, except here the feed is always a liquid. So, you have an evaporator feed which is a liquid sent to an evaporator where heat is supplied to remove some of the solvent and you end up with a dried product. So, let us look at this example problem for an evaporator, which would help us understand the fundamentals of performing material balances for this system. Unsweetened condensed milk is a shelf stable canned milk product. If 100 kilograms of fresh milk containing 87% water and the rest milk solids is condensed using an evaporator to remove 60% of the water from the fresh milk, you are asked to calculate the mass of water which is evaporated and the final mass and composition of condensed milk product. Please read the question one more time and make sure that you fully understand what information has been provided to you and what you need to calculate. We will now proceed to try and solve this problem, but I would strongly recommend that you pause the video and try solving it yourself and see whether you are having the understanding of how to go about it, and then see whether my calculations match with yours. So now let us see how I would solve this problem systematically to get the correct answer. So the problem statement says that 100 kilograms of fresh milk is entering into the evaporator. So we will use 100 kilograms of fresh milk as the basis. So let us write down the basis as 100 kilograms of fresh milk. Now let us try and draw a flow chart which represents the information that has been provided to us in this problem. So we have an evaporator which is fed with 100 kilograms of milk, and it is told that this milk contains 87% water and the rest is milk solids, which is 13% would be milk solids, and this evaporator gives you a final product where 60% of the water has been removed. So this would be your condensed milk, and water has been removed from the system as a vapor, and this is basically 60% of water fed. Using this information, let us see if we can calculate the amount of water which is evaporated and the final mass and composition of the condensed milk. So the problem statement tells you that 60% of the water which is entering into the system through the fresh milk is evaporated in the form of water vapor. So let us first calculate how much of water is actually entering into the system. That would be water entering is equal to 0.87 times 100 kilograms, which is 87 kilograms. So water evaporated would be 0.6 times 87 kilograms, which will give you a final value of 52.2 kilograms. Now we can write a total mass balance for the system which we looked at, which would be 100, which is the mass of fresh milk entering, is equal to W plus P, which is the masses of water leaving the system and the condensed milk which is leaving the system. So the final product, which is the condensed milk, would be 100 minus the amount of water which has been evaporated, which is 52.2. So you end up with 100 minus 52.2, which is 47.8 kilograms. So the final milk, condensed milk which is produced is 47.8 kilograms. We still need to calculate the composition of the milk. So writing a component balance for water, we would be able to get 0.87 times 100, which is entering through the fresh milk, is equal to X times 47.8, where X is the concentration of water in the condensed milk, plus 52.2, which is the mass of water which has been evaporated from the system. Solving this equation, we can calculate X as 87 minus 52.2 divided by 47.8, which is 0.728. So this would give you the mass fraction of water in the condensed milk. So now final answers are water evaporated is equal to 52.2 kilograms, final product produced which is the condensed milk is 47.8 kilograms, and this contains water at 0.728 kilograms per kilogram. So, this gives you the final answers. Let me walk you through my balance equations one more time so that there is some clarity. So, the total mass balance was reduced to input equals output because there are no reactions and there is no accumulation for a steady state process. So, we would have input which is 100 is equal to the summation of the two outputs which are W and P, and the component balance for water has been written as mass fraction of water in the input stream times the flow rate of water in the input stream, giving you the total mass of water entering the system, and this is equated to the mass of water leaving the system, which is two components. First one is water leaving as water evaporated from the evaporator, and the other is water leaving the system as a component of the condensed milk. So, these two have been written down as 52.2 and x times 47.8. Substituting all these values, we have calculated the value for x, and finally we understand the amount of water that has been evaporated and the amount of product which has been formed and the concentration of water in the condensed product. I hope you were able to follow this problem without much difficulty. So, we will move on to the next concept. We will conclude the lectures for today's class, and we will continue with more systems which are single units without reactions. Thank you and see you in the next lecture.